let's talk a little bit more about the connection between the polar coordinate system and the rectangular coordinate system. So as a quick little review, the connection between the polar coordinate system and the rectangular coordinate system, or the Cartesian coordinate system, can be seen really nicely if we just visually overlay a rectangular coordinate system on top of a polar coordinate system. So in the polar coordinate system, we define our points as a radius, a distance from the center of the coordinate system, or the origin, and an angle of displacement. So we go out to an angle, and then along the ray of that angle, we go a distance of our units. Now, if r were negative, it's a reflection across that same ray through the origin in the other direction. So we can see that that's what the rectangular coordinate system overlaid on top of it creates, is a connection using right triangle trig. So right here, this also has a rectangular location called XY, the rectangular coordinate systems. I have X on this image drawn up above, but it's also the same length of this adjacent edge on the triangle that we draw right here. And the connections we get by drawing in that triangle between X, Y, R, and theta are really useful because we can use them to convert between the two systems, and we can use them for graphing. We can do all kinds of things. So the connections that we get are that X is equal to R cosine of theta and Y is equal to R sine of theta. That comes out of the right triangle trig there. And then of course the Pythagorean theorem gives us that X squared plus Y squared equals R squared. And again, with right triangle trig, theta is equal to the inverse tangent of y over x. Now, we could also write that as the tangent of theta equals y over x, depending on what we're doing with it. So we could write that in its inverse trig form or in its just trig ratio form. Okay, so now let's take a look at a couple of examples where we utilize these relationships to convert between the two systems. So over here, on these examples, what I want to do on both of these examples, I want to convert from one system to the other. So on this first one, I want to convert the polar coordinates. So as I wrote here in the instructions, I want to take the polar coordinates that are given and rewrite them in their Cartesian or rectangular form. So take them from the r theta form, and let's write them in XY, equivalent XY form. So let's take a look, and I redrew this little image that we had on the previous screen. I just redrew that image here as a quick reference. So first thing let's do here is let's actually plot the polar coordinates. So also let's practice some plotting of polar coordinates. So we want to go to, it's kind of interesting because we look at the angle actually first. That tells us which ray to go to. So we want to go to 3 pi over 4. We could also have graphed this on a polar coordinate system, and you can use polar graph paper if you prefer. I just kind of sketched a rectangular coordinate system, and then I drew in the rays at pi over 4. Now, of course at 0 and pi over 2 and pi. So if we go from 0 and we go to 3 pi over 4, that would be the angle. And then the -6 is telling me that along that ray, rather than going out to 6 units along that ray, I'm going to reflect through the origin, and I'm going to go along the same ray, but this time a reflection through the origin. This would be 1, 2, 3, 4, 5, and 6. So I'm going to be plotted right here is going to be -6, 3 pi over 4. Now, one thing to note as I'm plotting that point right there, in the polar coordinate system, there are an infinite number of ways to describe this exact same point. So we went to -6, 3 pi over 4. But just a quick little note, if we wanted to rewrite it in a different form, this is also if we had rotated from 0, but we had gone in a clockwise manner instead of a counterclockwise manner, this would have taken us to +6 and negative pi over 4. We could also say that this is 6 and 7 pi over 4. And we could go on all day renaming this point using its different equivalent polar coordinates. Okay, so that's just kind of a side note, wanted to mention that, but we want to now connect this to its rectangular coordinate. So what would this be in the rectangular coordinate system? So let's go ahead, I'm going to go ahead and draw in the rectangular the rectangular coordinate system's already here. I want to draw in the right triangle that we could use to connect it. So we want to know what would be this x and what would be this y that would give me this equivalent point in the rectangular coordinate system. So what is the xy pair that would be plotted at that point? Okay, so a couple of things that we could do. One, we could use this reference triangle. We talked about how this was a negative pi over 4, and we could think about just the signs and the quadrant that we're in. Or we can just utilize the formulas that we derived, or that we had derived on the initial page when we were talking about our connections between rectangular and polar coordinates. So x is simply -6 times the cosine of 3 pi over 4, and y is -6 times the sine of 3 pi over 4. So x is equal to -6. The cosine of 3 pi over 4 is -√2 over 2. So this is positive 3√2. And y is equal to -6. The sine of 3 pi over 4 is a positive √2 over 2. And that's going to be a -3√2. So y is a -3√2 and x is a positive 3√2. And notice that does correspond with the quadrant that we're in for this polar coordinate. So again, we could have used right triangle trig or the formulas, but we see that the equivalent in polar coordinates, the equivalent rectangular coordinates or Cartesian coordinates are 3√2 and -3√2. And I ran into my little bubble right there. Okay, moved that thought bubble out of the way. And there is our answer. The rectangular equivalent to the polar ordered pair, -6, 3 pi over 4, is 3√2, -3√2. And we can see it plotted on the graph right there, overlaid between the rectangular coordinate system, the Cartesian coordinate system, and the polar coordinate system. Okay, let's do another one. Let's convert from this Cartesian point to the equivalent polar point. So in this case, let's go ahead and plot this Cartesian point. And just because we're plotting it, I'm going to go ahead and just grab the calculator there real quick. This is approximately -13.85, or 86 actually, and -8. Okay, so if we plot that point, that's going to be, let's make these 5, 10, 15. We're about in here, and then -8. So 5, 10, -8. We're about there. It's not perfect, but close enough. So -8 √3, -8. And let's do the same thing that we did before. Let's go ahead and draw in the right triangle. So this is -8 √3, -8, and we want to know what angle theta takes me to this point, and what would R be right here. So lots of ways to apply our right triangle trig, but we also have, and let me grab it, we also have our connections between the rectangular and polar coordinates, the generic equations that we've generated. So I just grabbed that little thought bubble that we were using just a minute ago, and just the connections that we have here in the relationships. And in this case, because we're converting from Cartesian over to polar, we can utilize and lean into these two relationships. The fact that we can find the angle by looking at the tangent ratio of y over x, and we can find the radius, the r value, or the hypotenuse of that triangle using Pythagorean theorem. So x squared plus y squared equals r squared. So let's start there. So we know that our x is -8, so -8 squared plus -8 √3 squared equals r squared. So we get 64 plus, let's see, this is going to be 64 times 3 equals r squared, and that's 256 equals r squared. So we take the square root, and r is equal to plus or minus 256. So r is plus or minus 16. Now, depending on how we want to define our polar coordinate, we actually have an infinite number of ways, as I mentioned before. Every ordered pair in the polar coordinate system has an infinite number of ways to describe it because of the way we're rotating around a circular system. So we could use a positive radius or a negative radius. We will come back to that in just a second. We'll probably use the positive radius, but we can come back to that in just a second and talk about the different iterations. So now let's get into and figure out what would be that angle. So the tangent of theta is equal to x over y. So it's equal to negative, I think I just said x over y, but it's actually y over x. So the tangent of theta is negative 8 over negative 8 root 3, which of course gives us tangent of theta is equal to positive 1 over root 3. So theta is equal to the inverse tangent, or we're looking for the angle whose tangent is 1 over root 3. Positive 1 over root 3. And what that gives me, of course, if I were to plug that into a calculator, or what that's going to give me is it's going to give me theta equals pi over 6, because it's going to be within the domain of the inverse tangent. So this is within negative pi over 2 to pi over 2, right? This is giving me that reference triangle. So I do have to think, let's make a little star on this. I do have to think about which quadrant I'm in. So make sure when we use this relationship that then we think about the quadrant and find the appropriate theta. I'm going to squeeze that into the bottom of the screen right there. Find the appropriate theta. So obviously pi over 6 is right here. This would be theta equals pi over 6. Now we could use that, but then we would have to adjust for the radius being negative so that we could go through the origin. So we can do that, absolutely. So we could say this was in our rectangular coordinate system. And let's write out, oh shoot, I didn't mean to do that. I kind of just wanted to get rid of that line, but I erased the whole y-axis, so we'll just come down below. So let's write out a few of the possibilities. So a few of the possibilities, we could absolutely say negative 16 and positive pi over 6. Now, of course, we could also write this in all kinds of other equivalent polar forms. So if we use pi over 6, that would take us to that radius as we have there. But if we wanted to take, let's take my highlighter here. If we wanted to go all the way and use a positive angle, we would, or that was a positive angle, a positive radius. If we wanted to go all the way and use a positive radius, so a positive 16, well, this equivalent ray in the third quadrant would be 7 pi over 6. Now, what if we wanted to use a negative angle but a positive radius? Well, we could go this direction and we could say this is equivalent to 16 and negative 5 pi over 6. Okay, that's probably enough examples on that one, but just wanted to illustrate really that we can go in, let's grab that. I have all my work down below. I just wanted to really illustrate that we could go, we have one single address, one single ordered pair in the rectangular coordinate system that describes this point. But because of the circular nature in the polar coordinate system, we actually have an infinite number of ways that we could describe this. We could just keep going, adding 2 pi to pi over 6, or 7 pi over 6, or negative 5 pi over 6, and keep going round and round and round and hitting that same point. And I just wanted to illustrate a few of those there. Those are all equivalent ways to write it. So as we came out with the radius being plus or minus 16 and that reference angle right there at pi over 6, we have to think about that and how that takes us into the proper quadrant and gets us to the equivalent rectangular coordinate. Okay, let's just continue our exploration of these polar coordinates in the polar coordinate system. So for these two examples, I grabbed some polar grids and let's go ahead and sketch the following sets. These are going to be sets of points. And let's go ahead and graph the following sets of points in the polar coordinate system. So on the first one, we are being asked to find all the thetas, all the angles, graph a set that includes all the angles that are greater than or equal to pi over 6 and less than pi over 2. So if we want to do that, let's think about where those rays are. So first of all, pi over 6 is this ray right here. And I'm going to go ahead and draw a solid red line on it because we actually want to include all the points that live on that ray, that have a radius that lies along that ray. Now, let's remember when I do that we also can have negative radiuses, so they could also go this direction. So let's include the ray that goes all the way down there. Then we want to make sure that our angles are all less than pi over 2. So pi over 2, and it's a strictly less than on that one. So that's strict less than. So let's use a dash line on that guy. So we're going to put in a dash line down along pi over 2. And now, of course, that's also going to go through the origin, because if the radiuses were negative, that could go through the origin in that direction. Now, we want to include everything that is greater than or equal to pi over 6 and less than pi over 2. So we want to include everything between these two rays, all of the polar points that are between these two rays. So they're going to be in here. I'm going to try to shade this as best I can with a highlighter here on the notebook. And it's going to bump right up to those two rays and include the pi over 6 ray, but not include the pi. Now that's going to keep going. That shading continues, so I will leave it that way. And it will also include this segment. So it will include all the polar points that are in my shaded region, including the ray pi over 6, but not including right up to, but not including the ray pi over 2. And so that would be the set of points that would be included who have an angle between pi over 6 and pi over 2, inclusive of pi over 6. Okay, let's think about this one. So what is this saying? This guy is now saying, this one's talking about the radius. So we want to include the set of all the points who have a radius greater than or equal to 2 and less than or equal to 5. So greater than or equal to 2, let's identify just r equals 2. R equals 2 is actually this circle. I might zoom in a little bit here. R equals 2 is this circle. So it's the circle at, I'm not getting my pen is getting wobbly. See if I can get it all the way around. And it's inclusive, so I'm using a solid line here. And then the radius of 5 is going to be all the points on this circle. Let's see, I got to come over here. I'm going to tweak my head. Let's see. So this is 1. There was 5 there as well. Make sure I connect along the right circle and all the way around for any. There was no restrictions given on the actual there was no restrictions given on the ray, on theta. So this is going to include everything in between greater than a radius of 2 and less than a radius of 5. And so let's go ahead and highlight all of that. I went a little out of my lines there, but I think you get the general idea. With shade, if I should have used my fill button here if I could have. And so this will include, this is the set of all the points that are in between those two circles in the polar coordinate system. Okay, so that's just another example of kind of thinking about what it means to be in the polar coordinate system between rays or between radiuses. Okay, for this next set of examples, we're just going to keep going on the same route that we were on, still working on these connections between polar and Cartesian. So we've connected the points, we've connected sets of points. Now let's talk about converting actual equations. So if I have an equation in polar form, let's talk about how to convert it into Cartesian form. And if I have a Cartesian or rectangular equation, let's talk about converting it into polar. Because we want to be able to work between these two systems, and sometimes we want to go back, be able to go back to the Cartesian, or maybe go from the Cartesian into the polar coordinate system, or vice versa. So let's talk about doing that. And again, I grabbed this little image again from the previous examples that we've been working with, where we have these 4 sets of this set of 4 equations that connect both our Cartesian to our rectangular and our rectangular to our Cartesian coordinate system. So we're gonna work with that relationship as we are playing with these. So if I've got r equals cosine of theta, r cosine of theta equals -4. Well, I recognize right here that this is equivalent to x. So this is just x equals -4. I didn't have to do a whole lot of work in this first one to convert to rectangular or Cartesian. And in the rectangular or the Cartesian coordinate system, this is just a vertical line. I won't go into the graphing, but it is just a vertical line, x equals -4. Okay, so I guess it was off the screen, but we literally just used that relationship right there, that x was equal to r cosine of theta. There was an r cosine of theta right there in the polar equation. I just replaced it with x. That was all I had to do. Okay, now let's look at one where we have a little bit more work to do. So we've got r equals 6 cosine of theta plus 8 sine of theta, and I don't have any r cosines or r sines, and I don't have just a definition for r over here. But here's the thing. I'm looking at this and I see r right here, and I see a cosine and a sine, and when I look at that and I think, you know what, if I were to multiply both sides of this equation by r, that's going to quickly give me some connections that I can use for substitutions, because that's going to give me r squared, which I know is x squared plus y squared, based on my relationship between the polar and the coordinate system. And I know that r cosine of theta, like we just used, is equal to x, and r sine of theta is equal to y. And I now have an equation in the rectangular or the Cartesian coordinate system. But what kind of an equation is it? So let's just practice a little bit. This is a conic section, and because we have 1x squared and 1y squared, I can move things around a little bit here, leave a little space for completing the square. It's a little review of conic sections, and I can add in some constants here to create a perfect square for x and for y. So here I will add in 9, so I'll have to add 9 in over here. Here I could add in 16, creating those perfect squares, and this is going to become x minus 3 quantity squared, y minus 4 quantity squared equals, excuse me, equals 25. And what we've ended up with here, and this is probably a much nicer way, right? These are equivalent equations. These are equivalent, but this is a circle of radius 5, and it is centered at 3, 4. That gives me kind of a nice way. If I wanted to graph it in the Cartesian coordinate system, in the rectangular coordinate system, I could easily graph it knowing that. So they are, of course, equivalent ways to write the rectangular or Cartesian equation, but kind of nice to do that little extra work on that conic section right there on that circle. Okay, let's keep going. What if we want to go the opposite direction? So what if we want to go from the Cartesian coordinate system into the polar coordinate system? Now, again, let's grab that image one more time. Here is the relationship. So we can just use this relationship. So for all the y's, I can replace them with r sine of theta. For all the x's, I can replace them with r cosine of theta. If I have any x squared plus y squareds, that's going to be equivalent to r squared. And tangent of theta is going to be equal to y over x. So if we had y over x's, we could replace those with tangent of theta. So in this case, we have just y equals 5. So what I'm going to do here is just recognize that I've got y, and that y is equivalent to r sine of theta. So this says r sine of theta equals 5, and that's my polar equation. And that's it. That was a simple substitution. Let's look at this one. This one will also be a simple substitution to start, but we'll get in and do a little bit more simplification. So let's take our x and our y, and we're going to replace x with our cosine of theta, so our cosine of theta minus 1 squared. We're going to replace our y with our sine of theta and square it and equal 1. Now we've made the conversion. This is now in polar. We've converted this over to a polar equation with polar coordinates, converted it from x's and y's into r's and thetas, but this cleans up a lot nicer. So let's get it cleaned up. R squared cosine squared of theta minus 2 r cosine of theta plus 1 plus r squared sine squared of theta equals 1. And notice here that I could subtract 1, and so the 1's would cancel, and then I'm going to group some things here. I get r cosine squared of theta plus r squared, I think I said r squared cosine squared of theta, r squared sine squared of theta minus 2r cosine of theta equals 0 now. Now over here, when I factor out the r squared, I get cosine squared of theta plus sine squared of theta. And of course, that's just 1. So that becomes just r squared minus 2r cosine of theta equals 0. Or r equals r squared equals 2r cosine of theta. But if I divide by r on both sides, I end up with r equals 2 cosine of theta. And that, again, notice that we went from this form into a nice little equivalent form that's a lot easier to work with in polar. So, we want to do that. We want to use our simplification tools, our expand. Here we wanted to expand and get that simplified after we made the conversions. So there's the nice polar equation that we can work with. And to end this video, I actually want to take that and one other one and graph it. So let's also, on this video, let's also practice just graphing polar curves. Okay, so we're kind of going through all of the different connections between the rectangular and the rectangular coordinate system and the polar coordinate system here. But what I want to do is I want to end this video just with also graphing in the polar coordinate system, because we've just connected this equation. Just on our previous example, we said that this equation had an equivalent polar equation of r equals 2 cosine of theta. So let's just pretend for a second like we didn't know this. We'll come back to this at the end. Let's pretend like we don't know that connection, and let's just graph this polar curve, r equals 2 cosine of theta. Now, on the previous video, we talked about how there's lots of ways to graph polar curves. One of them, and there, sort of actually, I'm going to do two of the methods combined. I actually think of them more like one method, just one's a visual way to do it, one's a tabular way to do it. So let's take r equals 2 cosine of theta. Let's graph that cosine curve, because hopefully we're pretty good at graphing trig functions. Let's graph that curve on the theta r coordinate system. And let's also make a little table down here. So here's our table. So we'll plot points. So in our table, we can plot points, and graphing is just a visual way to plot points. So let's take this curve, r equals 2 cosine of theta. So that's a cosine curve with an amplitude of 2. It still has the same, no adjustments on the period because it's just theta. So this is 2 pi over 2, 3 pi over 2. So a cosine curve is going to start here. It does start positive. It doesn't have any reflections, down to -2, 0 here. And so cosine curve is going to look something like that. One period of the cosine curve, of course, it goes on. But that's one period of the cosine curve. So that's a quick way to also generate the table if you wanted to do it just by plotting points and generate the table. So at 0, we're at 2. At pi over 2, we're at 0. At pi, we're at -2. At 3 pi over 2, we're at 0. And at 2 pi, we're back at 2. So that does give us some ordered pairs to plot as well. So I like the graph, though, because it gives me that real image of what's happening in between 0 and pi over 2, for instance. So as my angle, so we're going to start at 0, and we're going to start our angle over here at 0, and we're going to increase the angle and plot points as we go. So at 0, we are at 2. So we're plotting the point right there with a radius of 2 and an angle of rotation from the positive 0. An angle of rotation of 0. So we're going to be at 2. And then from 2, our radius decreases till it gets down to 0 by the time we're at pi over 2. So at pi over 2, we have a radius of 0. And throughout this whole little region, as the angle increases from 0, so as the angle is going from 0 up to pi over 2, the radius is decreasing down to 0. So what would that look like in the polar coordinate system? Well, remember, these circles represent the radius. So as we are going along, our radius, as we are increasing, right, you got to think in a circular motion. As our radius is increasing, as our angle is increasing, our radius is decreasing. So actually, I think my first picture was better. So as my radius is increasing, there we go. Okay, then what happens? So that would be segment 1. So then as we go from pi over 2 to pi, so from pi over 2, so now we're moving from pi over 2 to pi, notice that the radiuses are all negative. So in this region, the radiuses are all negative. By the time we get to pi over 2, the radius is a -2. So we're actually back over here again. So we're back over here because at pi, we have a radius of -2. So we reflect through the origin 2 units in the other direction. So that means that as our angle is going from pi over 2 to pi, we're actually going to be graphing in this quadrant because we have the negative radiuses. So, and on that region, the radius in size is going from 0 back out to 2. So it's looking like this. So it's going from 0 back out to 2. We have those negative radiuses, which is why we are reflecting through from the second quadrant into the fourth quadrant. So that's representing the second segment of my little piece here. We could also, I think we were also going along here. So check, 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 plotted those points as well. Now we got to go from pi. So now we're over here at pi. Erase my picture. Now we're over here at pi, and from pi to 3 pi over 2, we still have negative radiuses, but they are decreasing in magnitude from -2 to 0. So while we're graphing over here, while our rays are over here, the negative radiuses send me up here to graph in this first quadrant. So what's going to happen is, I guess maybe I could get a different color to show what's happening on this segment. So from here to here, I don't know, that blue is not the right color to use. Let's get rid of that and try something else. Let's try maybe gold. So from here to here, that's the third segment. So the third segment is retracing the first segment because it's going from pi. So let's change this color over here as well. So because we're going from pi, oh my goodness, why did it delete? I think when I scribbled, it deleted it for me. So we're going from pi to 3 pi over 2, which technically, you know, the rays are increasing in this direction, but because of the negative radiuses, we're reflecting and plotting points up in this quadrant. Okay, then we keep going. So I'll do this also in gold. So from 3 pi over 2 to 2 pi, our fourth segment has, so as we plot from 3 pi over 2 to 2 pi, our fourth segment is also tracing out 2 again. So as we go, we actually go through this circle 2 times. So something to note right here, we actually trace this circle. It is a circle. We trace the circle 2 times from 0 to 2 pi as we go increase our theta from 0 to 2 pi. So we end up with this circle that gets traced through 2 different times. And I wanted to just talk about this last little piece here, that connection that we started with, that connection back to that circle. That is a circle of radius 1 with a center at 1, 0. And notice that this exactly, if we were to overlay the coordinate system right here, that's exactly what we have. We have a circle of radius 1. This is a circle with a radius of 1 centered at 1, 0. And so you can see, like, if we think about overlaying the coordinate system, we connected those two equations using polar coordinates and rectangular coordinates. We connected those two, and we end up with this nice little polar graph that connects right back to its equivalent Cartesian equation of a circle. Okay, so I know this video is going a little bit long, but let's just do one more example. So let's take a look at, and I did some work ahead of time to save a little bit of time here. So let's take r equals 3 minus 6 sine of theta, and let's graph this polar equation in the polar coordinate system. So I just went ahead and did a quick graph of this. So this has a period of 2 pi, it has an amplitude of 6, there's a vertical shift up 3, and it has a reflection because of the minus. So this is the graph, and we can use this graph to give us a quick image of what we have going on over here. And then I want to connect it to families of curves so we can see what's happening with the families of curves. So in this particular case, there are 2 spots that I'm going to need when I graph, because notice from the first segment, from here to here, we have a positive radius. So we start at 3, and we have a positive radius at 0, 3. So when we have an angle of 0, we're at 3. But the radius decreases till it gets to 0, and then it goes negative. And we're going to need to know what these points are. So what would these points be? Well, that would be when r equals 0. So we set 3 minus 6 sine of theta equal to 0. So negative 6 sine of theta equals negative 3 sine of theta equals 1/2. So when does that occur? Well, the sine of theta equals 1/2 at pi over 6 and again at 5 pi over 6. So this point, and that's going to be useful for me when I'm plotting points, is at pi over 6 and at 5 pi over 6. So this point right here is pi over 6, and this point right here is 5 pi over 6. So let's label that on my graph. So here's pi over 6, here's 5 pi over 6. I'm also going to circle them on my polar coordinate system. And I know when I'm graphing that I start with a positive radius, but that positive radius spins down till it gets to 0 at pi over 6. So I'm going to zoom in here. So it's decreasing down to 0. So we have something that looks like that. And then from pi over 6 to pi over 2. So this next little segment of the graph, from pi over 6 to pi over 2, I have negative radiuses. So I'm not actually graphing here. I'm going to be graphing in the reflection. I'm going to be graphing from 7 pi over 6. So if I reflect that through 7 pi over 6 to 3 pi over 2. So I'm graphing here and I'm going out to a negative 3. So by the time I get to pi over 2, I'm going to be at negative 3, which would be plotted down here through the origin, and my radiuses in size are going back out to that radius of 3. So they're getting, the radiuses in size are getting larger, but they were reflected, which is why we're plotting down here in the third quadrant. And then from pi over 2 to pi, so coming up that last piece, from pi over 2, so as we're going from pi over 2 let's go to 5 pi over 6. Let's stop at 5 pi over 6 first. So remember, we're stopping at those 2 points. So at from pi over 2 to 5 pi over 6, we're actually going to be plotting in the fourth quadrant because of the negative radiuses. So we're going to be in size, decreasing our radius back down to 0, but because of the reflection, we were in the opposite quadrant. Now from 5 pi over 6 to pi, we go back out to 3. So now and those are positive radiuses. So now from 5 pi over 6, let's get 3 plotted before I start going. There we go. So we are going to come back out to a radius of 3. So our radius comes back out. Then from pi to 3 pi over 2, the radius just continues as we go from pi. So now we're continuing to move here, move this far. Now from pi all the way until we get to 3 pi over 2, we're going to increase our radius all the way out to 9. So by the time we get down here, we're going to be at 9, and our radius is just increasing out as we go across those angles. And then the radius from 3 pi over 2 to 2 pi, the radius is going to decrease back down. There's definite symmetry here as well. So the radius is going to decrease back down to 3. Now that's not the most beautiful picture. Let's get off some of my sketches here as we were going. It's not the most beautiful picture. I think I'm actually better on a whiteboard than I am drawing polar graphs on my notebook, but we get the general shape. This is what we call an inner loop. This is an inner loop limicon. So inner loop limicon. Let's see if I spelled that right. So we could absolutely have gotten this from our graph, just like we did. And I wanted to show you how you can use that graph to even get those little inner loops and things. We can absolutely have gotten this from our graph, but we could also have caught this and looked at this form right here and compared it to our families of curves and identified that it was going to be an inner loop limicon, and then plotted points to get the direction and the exact orientation. So let's grab those family of curves just to wrap up this video. Okay, I just grabbed our reference sheet just to connect back to families of curves. So clearly we were able to graph this just using our sophisticated, what I like to think of as a more sophisticated plotting of points. We used the r versus theta curve, took that, graphed it, used that curve to give us an idea of what the polar curve was going to look like. But this does fit a limicon. Oh, I did spell it wrong. Spelling, limicon. This is an inner loop limicon, because take a look at this. We've got r equals 3 minus 6 sine of theta. So that's r equals a plus or minus b sine of theta. So it fits that pattern. There are a couple different iterations of that pattern. But the inner loop limicons come when a and b are both greater than 0. And again, the plus or minus is not relevant to b. B is the magnitude that we're looking at right here. So a is, in this case, 3, and b is 6. And if a is less than b, that's what gives us those inner loop limicons. So we can see from just the family of curves, if we were using our family of curves, we would know that it was an inner loop limicon. We would know that it looks something like that. Now, how do we get the orientation? Well, that's where we actually need to plot some points. So we can use the families of curves to give us an idea of what the general shape is, and then we plot a few points to get us into the actual curve. So we could have recognized this was an inner loop limicon, and then we could have followed up by what we did here, maybe gone a little bit faster, kind of already knowing what the shape was going to be like. So use these skills, put these skills all together, because we're definitely going to head into calculus from here. We're going to take these curves and we're going to compute calculus. Like, you know, a good question would be, what's the area of that inner loop, right? Like that would be a fun question to be able to answer, and we'll be able to do that after the next section. So, but we do need to know how to graph these. So pull all your skills together. Hopefully this was a good review video. I know it went a little long and we covered lots of review in this video, but hopefully most of it was review.